Okay, so let's proceed with our understanding in the previous video where we did the naive approach of going, towards the left and right of the rectangle of interest, and trying to find how far it can be extended consecutively, trying to find a rectangle of either the same height or larger height, right? So for 8, we stopped at 8 because there was nothing towards the left to extend it, but towards the right, there was a smaller rectangle, right? So nothing was extending 8. For 4, 8 was extending 8, and that's where it stopped. And then 6 was higher, so that extended 4. 5 was higher, 5 extended, 7 was higher, 7 extended 4, and 3 was lower, so it wasn't extending 4, right? So we calculated that it would take us two for loops, going left and right, and it would be ending up being a O of n square kind of approach, right? So let's build upon that intuition and understanding, right? So let's say let's say I have CDs or rectangles in increasing, right? So let's say I have all of them sort of increasing here, right? Uh, let's call them maybe 3, 4, 5, 6, right? So we'll number the indices 0, 1, 2, 3, right? So if I have an increasing set of rectangles, so each new one uh, will be extending the all the previous ones as long as it's greater than the previous one, right? Because it's increasing sequence, right? So 4 would be extending 3, 5 would be extending 4 and 3, 6 would be extending 5, 4 and 3, right? So each one of them is extending all of the others, right? So the intuition that we had on in the previous approach was for the current rectangle, right? For this rectangle, we try to find something which is smaller than this in on either side, on left and on right, right? So we'll look at the same approach here. So now all these rectangles are in increasing order. So we'll use a small trick here wherein we'll stop at the last so-called non-index, right? So we'll stop at 4 and let's call that 0, right? There is nothing here, right? So 0. So all the rectangles towards it left would be less than that, so that we can process to sort of determine the solid area, right? So now uh, that is our so-called I, or in the previous approach what we were using. So let's say we are looking at this. So now let's say um, uh, we are using this approach with this current rectangle of interest, right? So 6 is what we want to estimate what would be the size of this solid area, right? So the first immediate rectangle, since it's increasing, right? So we know that if we let's say sort of push it on a stack, right? So on an increasing stack, right? So the first element that would be smaller than this would be the element immediately to the left of it, right? Or the element that is next on the stack, right? So which is this element here whose index is 4, right? And since we don't have any element on the right, so which is smaller, so we are taking this dummy element and we are considering that as the element that is smaller. So if we use an intuition wherein uh, we have to stop at these two indices, right? And these two do not include, or they don't sort of extend the current rectangle, right? Like we saw. So the ones that don't extend, we don't include, right? Let's say when we were looking at 5, so 4 and 3 were not included, right? So the only rectangles that were included were 6, 5, and 7, right? So 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 to get the to get the right index, right? So 4 is the one that is smaller on the right side, right? So this is the right side, and the left side is 5, which is index 2, right? So 4 minus 2, and then so these are exclusive intervals, right? So 4 minus 2, we have to subtract one more so that we get the right count in between. So in between these two. So 4 minus 2 minus 1 would essentially be just 1, right? So that is the number of rectangles that would be extending this, which is just 1, which is times 6 is 6, right? So same thing for the next one, right? So for 5, I have 4 and 1, right? So 4 minus 1, right? Minus 1, right? So that would be uh, I have 2 times 5, right? 2 times 5 is 10, which makes sense, right? So 5 is extended by this, and which whole, if you look at the area, this whole area is just 5 times 2, right? Each unit. And then for 4, it is sandwiched, so that the smallest rectangle to the left of it is this, which is 0. So, and to the right is this our dummy, right? So 4 minus 0 minus 1, and it comes out to be 3. So 3 times 4 is 12, right? And then uh, for the last one, right, for 3, right, we don't have any rectangle to the left of it. So what we did, or what we'll do here, is we'll just use this count here, right? Since it starts with 0, and we know that the only rectangle that's going to end is this guy. So we just have one interval, right, on the right side. So we use that, and we would say, okay, so 4 times 3 equals 12, right? And if we look at this whole area, so this is 3 height and 4, right? 3 times 4 is 12, right? So that gives us an intuition. So this is the right, and this is the left, right? So the right limit minus the left limit, and then you have to subtract 1 out of that. And the same thing can be true for a decreasing sequence too, right? So let me extend this towards the right a little bit so we can see that. So let's say we have uh, a decreasing sequence, right? So say we have 6, and then 5, and then 4, and then 3, right? So we have 4 see rectangles in decreasing sequence, and ordered from 0, 1, 2, 3, and uh, and 0, 1, 2, and 3, right? So uh, we know that with our intuition, that every rectangle that we look at, we try to find uh, the smaller one towards its left and a smaller one towards its right. And if it's in decreasing, every new rectangle is going to stop the growth of the previous rectangle, right? So 5 is smaller, so it can't extend this. 4 is smaller, so it won't extend 5, and 3 is smaller, so it won't. So every new rectangle will stop. So we have to calculate at every point, basically, pretty much. So, and we know here, so nothing is there towards the left of this rectangle, right? So for this uh, rectangle, when we are looking at, the one that is stopping it is this guy, right? So the index of this guy, which was the right in our case, right? So right hand side is 1, right? And if there's nothing towards the left, so we just use that as our limit, and then we multiply that by 6, right? So that would be 6. Okay, and then we go to so we calculate that for this particular rectangle, right? So this is gone out of the conclusion here. So now we go to this guy, right? So what's the rectangle that's stopping it is this one, right? So the rectangle that is smaller than this, and we know that uh, if we were building up sort of like an increasing stack, so there is right now there is probably nothing on the stack, right? So if there's nothing on the stack, so we just have the right limit, right? So there's nothing on the left limit here. So we use just our right limit, and we say, okay, so 2 times 5 is equal to 10, right? So we are just using our right limits here, right? So right limits, and then we come to this 4 here, right? So this 4 has the right limit of 3. So 4 times 3 is 12. It's the same thing, right? So, and if you look at the area here, is comes out to be 12, right? 4 times 3, and then we know. So, and all of these are just popped out of the stack. So we don't have any one if you're maintaining a stack of increasing buildings. So there's no building at this moment. So the only building is the building under consideration, right? So now we are looking at 3, right? And there is no other uh, building towards its right, and this is the only building in consideration. So uh, what we do is we take uh, the dummy element here, right? So basically we would take the index that's after this, and so we would multiply that by the height of this, right? So that would be uh, uh, 4 times times 3, right? So that would be 12 as well. Actually, this should have been 3 times 4. So that's the height, right? So this is the height and this is the limit, right? So height and limit. So let's look at a little more complicated example in the next video, and that would make more sense.